Greetings and welcome to the 20th Linear Algebra Clinic. Today's clinic is going to focus on problems dealing with the matrix of a linear transformation. We begin by considering the linear operator on R2 given and the basis S. We are going to show that the matrix, we're going to find the matrix representation of G relative to S. And then verify that that matrix times the coordinate vector for V with respect to S is equal to the matrix representation, or the coordinate vector, I'm sorry, of G of V, right, for the given vector, okay? So to find the matrix representation, what we want to do is transform each of the basis elements. Let's start by transforming 1, 3. Right, so by the transformation, that's going to be 2 times 1 minus 7 times 3. And then 4 times 1 plus 3 times 3. Right, so that is negative 19, 13. Right now, I'm going to write that as A1 times 1, 3. Right, so now we want to write as a linear combination of the basis elements. We're going to do the same thing now for the second basis element, the vector 2, 5. And so we see that this is going to give us negative 31, 23. And now we want to write that as a linear combination. Let's say B1 times 1, 3 plus B2 times 2, 5. Well, now we have two systems to solve. Coefficient matrix will be 1, 2. I'm sorry, 1, 3, 2, 5. Now let's augment it with negative 19, 13. But we can actually now do a double augment. Let's go ahead and augment it with the other transformation, right? Negative 31, 23. And let's row reduce this. So what we find is this is the solution for A, right? A1, A2. This is the solution for B, right? B1, B2. Together, they form our matrix representation with respect to the basis S. I don't know why I wrote a part B there. That was not part B. This is part B. Right now we're given the vector V. All right, so the first thing we want to do is find the coordinate vector for that. So let's go same coefficient matrix, but now augmented with V. We'll reduce that. And so this means that our coordinate vector of V with respect to S is negative 26, 15. So now what we're going to do, right, is we're going to take this G up here. Okay, so we're going to take that. We have to multiply it by V. Okay, let's see what we get when we do this product. All right, so do out the product, negative 131, 80. We now want to find G of V. Okay, well, that is G of 4, negative 3. Right, you'll find that that is 29.7. Right, so again, we want to find its coordinates with respect to S. Okay, and we will reduce this, we're going to get negative 131 and 80. Right, so that means that the coordinate vector of G of V with respect to S is negative 131 and 80, which is exactly what we got above, right? So therefore, the matrix representation of G with respect to S times the coordinate vector of V with respect to S is equal to the coordinate vector of G of V with respect to S. Right, and that is what we wanted to verify. Okay. We want to do the same thing, but now we have a different operator and a different basis. All right, so we start the same way. So transform each of the basis elements and then write them as linear combinations, right? So transformation of 1, 1, 1 is 3, negative 3, 3. The transformation of 1, 1, 0, 2, negative 3, 3. And the transformation of 1, 0, 0 is 0, 1, 3. Let's set up our matrix. Right, so the first augment will be 3, negative 3, 3. 3, negative 3, 3. Second augment, 2, negative 3, 3. Third augment, 0, 1, 3. And so row reduce this. Right, and then this is what we get. That should be a 6. That's that, and then 3 and -2. Okay, therefore, matrix representation of G with respect to S is that matrix right there. Right now, what we want to do is verify that equality for any vector V. Right, so what we do is we say let V be an arbitrary 3 vector, so X, Y, Z. We need to find the coordinate vector. So we set this augmented matrix. When we reduce it, get Z, Y minus Z, and X minus Y. Right. So clearly the coordinate vector, Z, Y minus Z, and X minus Y. So now let's go ahead and multiply our matrix times that coordinate vector. And again, I'm going to use the power of technology so I don't have to rewrite it. All right, throughout that product, 3x, negative 2x minus 4y, negative x plus 6y plus z. Now to find g of v. Well, we already know what that is, right? That is 2y plus z, x minus 4y, 3x. Right, so we now need to get that coordinate vector. With respect to x. Or with respect to s rather, right? So that's this. Reduces. That obviously means then that our coordinate vector g of v with respect to s is this. And that confirms the equation. Okay, so here we're told the set e to the 3t, t times e to the 3t, and t squared times e to the 3t is a basis of a vector space V on functions from the real numbers to the real numbers. We're going to say D is the differential operator on V. We wish to find the matrix representation of D relative to S. Right, so what we're going to do, right, we pass each of the base elements through the operator. Okay, there they are. Right, so now let's set up our we actually don't need to set up a matrix here, right? Because if we just set up our linear combinations for each one, right? So there is that. Then we have this one. And then have this one. We can easily see the solution, right? We can just eyeball this solution. Here, alpha 1 has to be 3. The other two are 0, right? So the first column would have to be 3, 0, 0. But if we look at the second column, it's going to be the solutions of the betas, right? Well, beta 1 has to be 1, beta 2 has to be 3, beta 3 is 0. So 1, 3, 0. Right, and then you can easily see then that the gamma solutions 0, 2, 3. There is our matrix representation. Okay. So we're told that T is a linear operator from V into V. S is a finite basis of V. We want to prove, right? So we want to prove the equation that we're working with, right? In 1 and 2, okay. Let's go ahead and define our basis. So it's going to be finite, right? So we're going to say it has elements U1, U2 up through UN. So we're just going to assume it has n elements. Right, and this is our basis for V. What this means, for any vector V in V, right, we can write V as a linear combination of the U's. Okay, and UN, which means that our coordinate vector for V with respect to S, K1, K2, down to Kn, right? Right, so for each U sub I, suppose, or I should say for each U sub I in S, suppose T U sub I equals some linear combination of the U's. I should call them, I'm sorry, let me rewrite that. Subscript should be I1, AI1, U1 plus AI2, U2 plus so on and so forth, AIN, UN, right? Because we have a total of I's. Thus, what this gives us is our matrix representation of T is the matrix Tij, right, where the ij component, right, is A sub ji. Right, has to be ji because these are columns, right? So AI1, AI2, AIN forms the ith column of our matrix. Right. Therefore, the ith entry of this, I should say it's the ij entry, isn't it? This sum right here, TIL times KL. No, this is the ith entry, I'm sorry. Because that's going to be a vector. Right, so this is going to now equal L equals 1 to n summation. of A Li times KL. Now, if we look at T of V, this is T of K1U1 plus K2U2 plus so on and so forth, KN-UN, which because T is linear, is this. However, U1 is this. Right? So on and so forth until we get up to K sub n, right? And then UN is this. This means that the ith entry of the coordinate vector for T of V with respect to F is the summation L equals 1 to N, right? ALI times KL. So comparing the entries of T with respect to S, right? So the matrix representation of T with respect to S times the coordinate vector of V with respect to S and the coordinate vector T of V with respect to S, we find they are identical, all of them, which of course means that the two must be equal. As desired. All right, so we've been working with operators so far. Right, that is a transformation from a vector space into the same vector space. And a single basis. Well, now, next problem is going to give us a mapping from a vector space into a different vector space. Right, relative, obviously, we're going to have two separate bases. Right, but the process itself is the same. What we want to do is take each element of the basis of the codomain, transform it, and then we will write it as a linear combination of the basis elements of the codomain. So there are the transformations The basis elements. Now we need to write these as linear combinations. Oops, there is a typo, S prime. I don't know what happened there. That is really wrong. Let me fix that. I don't know what happened. Okay, this. Excuse me for just a second. Sorry about that, corrected now. Right, so it should be 1, 3, 2, 5. So 1, 3, 2, 5. Right, now, of course, we augment it. 1, negative 1. Second augment. 5, negative 4. Third augment. 3, 1. Row reduce this. And we get negative 7, 4 in the first augment. Negative 33, 19 in the second. And negative 13, 8 in the third. All right, so this matrix here, right, the matrix representation with respect to S and S prime, negative 7, 4, negative 33, 19, right, negative 13, and 8. Right, then what we wanted to do is verify. I will leave that to the viewer because I am out of time. So there was another problem, but it's very similar to this problem here. So we'll just go ahead and say that's it. So that is where I will end today's clinic. I thank everyone for attending. Thank you for watching. I will see everyone in the next clinic.